Let me give you an application, an economic application of this. Recall the Cobb-Douglas production function is this. Where capital A is some positive parameter, little a is some number between 0 and 1, and little b is between 0 and 1. This is a nonlinear function. However, it's possible to linearize this function if you take the logarithms of both sides. For example, the logarithm of q must be equal to the logarithm of this, a times k to the a times l to the b. You just take the logarithms of both sides. And if we apply this rule number 1, and actually we're applying this an extended rule number 1. If you have 3 terms, let me just write this. If you have the logarithm of u times v times w, what is that equal to? What would you guess? If you have 3 terms in there, u, v times w, u, v, and w are variables. You just add them, each of them. So it's the log of u plus the log of v plus the log of w. Okay. Well, let's apply this extended rule number 1 to this right-hand side expression here. So this is the logarithm of a plus the logarithm of k to the a plus the logarithm of l to the b. Because you have 3 terms, a, k to the a, l to the b. So you can do that. And you can break these 2 terms down further. So this is the logarithm of a. I'll just repeat that first term. But this second term, you can bring this little a down, plus little a times the logarithm of k, plus b times the logarithm of l. And what's nice about this expression is this is a nice linear expression in terms of the logarithms of the variables. This is log q equals some constant, the log of a, plus little a times the log of k, plus little b times the log of l. And are some of you taking 351? So you know about linear regression. And what you could do is you could, if you have, for example, a time series expression, you have quantity for several different time periods. You have measures of the capital stock for several different time periods. You have measures of the labor stock over time. Then what you could do is measure output not in its natural values, but in its logarithmic values. And regress that on the logarithm of capital and the logarithm of labor. You could do this linear regression of log q on log k and log l. And then the coefficients you get, little a and little b, will just be the coefficients from doing a linear regression. Only you're doing your regression analysis in the logarithms of the variables instead of their natural values. And the constant you get in your regression will just be interpreted as the log of a. Okay, so this has a great practical significance. Sometimes you could take nonlinear functions and you could use a logarithmic transformation to linearize the equations and then estimate them in a straightforward way using linear regression.